This is Math 251, section 12.3. And in this section, we're going to be starting to do the calculus of multivariable functions. Specifically, we'll be starting with domain and range, but really our primary focus in this section is going to be limits. Eventually, we'll also do derivatives and integrals of these multivariable functions. All right, so let's start with domain and range. If you've got a function of two variables, f of x and y, equal to z, the domain is going to be all of the x and y values that can be plugged into the function. So all possible values of x and y, meaning your domain is actually going to be a set of ordered pairs. Well, if you have a whole set of ordered pairs, they end up forming a region in two space. So my domain may have some region R in two space defined as the legal values or the possible values of x and y. The range is the output. That's just z. So the range will simply be all possible values of z and that's just going to be some interval, right? Z is just a one variable, so it would just be some potentially open or closed interval from A to B. I drew it closed, but it could be either. All right. What about if we have a function of three variables, x, y, and z, equaling w? In this case, our domain is going to be all the possible values of x and y and z, or in other words, all possible points x, y, and z, that's our inputs. Now, a set of three-dimensional points, if you put a whole bunch of them together, is going to form some sort of solid in three space. So some sort of a three-dimensional solid. The range is going to be all the w values, and again, since that's just a single variable, that's just going to be some kind of an interval. I'll draw it open this time, but it can be open, closed, whatever the circumstances demand. All right, so our new and different thing here when we talk about domain and range is going to mainly be with the domain. Instead of just an interval of values, domain is going to be a whole region if there are two independent variables, and an entire three-dimensional solid if we have three independent variables. All right, so for the next couple of problems, we're just going to go ahead and identify the domain and then try to sketch it, and then see what we can figure out on the range as well. So for part A, f of x and y is equal to 1 over x plus y minus 2. Now, just like any other function, we know that anytime we have a fraction, the denominator can't be 0. So as far as my domain, x plus y minus 2 is not equal to 0. So x plus y is not equal to 2. Any other points, except the points specifically on this line, x plus y equal 2, are perfectly okay. So the actual domain would be all points not on the line, x plus y equals 2. And if you were going to sketch that, that's just a line with both x and y intercepts being 2. The line would look like this, right? And I'm going to draw that as a dotted line. to indicate that it's not part of my domain. And the domain is everything else. So everything on both sides of that line would be the sketch of the domain. You have to play around with that just a little bit to get Maple to show you that, but you actually can. I'm going to go ahead and show you a graph of this function in Maple, and we're going to take a look, and we should be able to see how that line, x plus y equals 2, is missing from the domain. All right, here's the graph. You'll notice I did an implicit plot 3D just so I could control all three of my variables I wanted to define my window. And here's our function, 1 over x plus y minus 2. I've set up a window, and I did do a little bit of extra point plotting here. I've got num points as 5,000 points to plot, and I set my style as surface. And here's the graph it gave me. A couple things about this graph. First of all, if I kind of look at it, side view here. This vertical line here is actually non-existent. It's like an asymptote. It's just a three-dimensional asymptote, and you probably remember your calculator often tries to graph asymptotes even though they don't exist. This program is going to do something similar. So we're going to ignore that, what looks like a vertical line from this perspective, although it's a whole vertical plane when I rotate. So there's my graph. It's actually this kind of downward curving sheet, and then this upward curving sheet are the two pieces of my graph. And then I'm going to look at kind of a top-down view here. And what I'm going to ask you to notice, if I can get it lined up just right here, there we go, I can see the gap. See that little gap right here? That little gap shows you where the function doesn't exist. There is no z value. And notice that's an x-intercept of 2 right there. That's a y-intercept of 2. So that's exactly the line that we were talking about. X plus y equals 2 is excluded from the domain. There are no z values for points on that line. All right, let's go back to pencil paper here for a few minutes, and let's look at another one. Oops, pencil paper, come here. There we go. All right, part B is a function of 3 variables. So that's the output is the square root of 9. Oh, excuse me, I forgot to do the range on this one. Let's go back and do that. Anytime I've got a fraction, one thing I do want to notice is that the only way a fraction can be 0 is if the numerator is 0. So I do know that there's no z values that will ever equal 0 here. I believe, however, the z's can be anything else. If these were negative numbers, right, I could get any negative number, small or large, in the denominator. And if these were positive numbers, I could get any positive number, small or large, in the denominator. And so, in fact, my range is going to be any z except for 0. That is from negative infinity to 0 and from 0 to infinity. So there's my domain and range for that problem. Actually, if I click back to Maple again real quick, you can see that here as well. Let me go back up. There we go. Let me go back to that side view again. If I go to a side view, and maybe I'll change the color to make it a little easier to see. Do this in red. There we go. You can kind of see now from the side view that over here this stays just above the xy plane, never hits z equals 0. And this one over here, if I just get my perspective here, stays just below, just about had it, stays just below the xy plane. Z is never 0. However, based on this side view, we can see that this sheet is going to keep on going up forever toward positive infinity. So this side goes from 0 to positive infinity. And then this side here goes from 0 down toward negative infinity along this asymptotic type of plane. So you can see the range in the graph as well. All right, now let's go ahead and go back to our pencil and paper. All right, part B. We had this function. This time it's a function of 3 variables. And it's the square root of 9 minus x squared minus y squared minus z squared. My domain is going to be the condition that what's under that radical has to be positive, right? It's going to be a real valued function. You can't have a negative under the radical. So as far as the domain is concerned, I'm going to say 9 minus x squared minus y squared minus z squared has to be greater than, or it actually could be equal to 0. I certainly can take the square root of 0. All right, if I move all of the variables to the right-hand side, that says that 9 is greater than or equal to x squared plus y squared plus z squared. With the equality, this would be a sphere of radius 3. And since this is all less than or equal to that, we're looking at the inside of a sphere of radius 3. So if I were to sketch my domain, there's that sphere of radius 3 from the 9, and I would shade in everything inside of it. All of those points are legitimate values to plug into our function. By the way, notice up here I used a dotted line to show that we don't have points on that line. Here I did my sphere primarily in solid lines. I only used the dotted line to show perspective. And that says that we do include the points right on the boundary. All right, what about the range? Well, a typical square root function, right? Square root of anything is greater than or equal to 0 when I'm taking a positive square root, which I am here. So I'm going to say, if this is w, w is greater than or equal to 0. And so my range is the interval from 0 to infinity. I can't graph this one because it would require a 4-dimensional graph, right? I'd have to have x, y, and z as input points, w as an output point, and we don't have 4 dimensions to work with in our world. So we can't actually graph this function, but we can still determine its domain and range. All right, let's go ahead and start talking about some limits. First of all, I need a couple of definitions here on page 15. A region R, which is a subset, that's a subset symbol, subset of R2, 2 space, is called closed if it includes the boundary, and open if it doesn't. So just as a quick little picture, that region would be considered closed because I've included the boundary of the circle. That region would be considered open because I have not included the boundary. All right, next definition is probably pretty obvious, but we'll go through it here. A point on the boundary of R is, surprise, surprise, called a boundary point. And the other points in R are called the interior points. Now, one thing it probably is worth pausing to notice is it doesn't matter if the boundary is closed or open. Any point on that boundary would still be considered a boundary point. Points that aren't on the boundary would be the interior points. All right, to evaluate a limit, At an interior point of the domain, you should simply be able to substitute the values in and be done. Nothing bad should happen. You shouldn't get anything undefined. No indeterminate forms. Plug in your numbers and you're there. Okay. The boundary points are the interesting ones, and of course the ones that require a bit more work. At a boundary point of the domain, typically you have to do some work. Usually we have to do some algebra. All right, we're going to pull back on some of the knowledge of limits that I know you all have lurking back in your heads from Calc 1, maybe a little bit of Calc 2. But I am sympathetic to the fact that you haven't done them for a while, so I'll try to remind you as we go along. All right, in example 2, for each of these examples, we'd like to sketch the domain, identify the point being approached as either boundary or interior, and then find the limit. So in example A, as far as the domain, I just have to be sure that that denominator doesn't equal 0. So y can't be equal to 4. To sketch that domain, I would exclude the line y equals 4, and my domain would be everything else. Again, please be sure you're using those dotted lines to show an open boundary in this case. We can't include any points on the line y equal 4. Everything else is my domain. All right, identify the point being approached as either boundary or interior. In this case, I'm approaching the point 2, 5. So 2, 5 would be up here. It's completely inside my region. It's not on that open boundary, that line y equal 4. So this is an interior point. With interior points, limits should be easy. We should just be able to plug in our numbers. So doing the limit as the point xy approaches the point 2, 5, I am just going to go ahead and plug in my numbers. That would be 2 squared plus 3 over 5 minus 4 is 7. And this is telling me that there's essentially like a continuous situation on the graph. At 2, 5, 7, the graph just looks like perfectly smooth and normal. Nothing weird is happening. There's no asymptotic behavior, no missing points, nothing like that. All right, let's try a couple more. In part B, we have the function 2x squared plus 7xy minus 4y squared over 2x minus y, and we want the limit as the point xy approaches the point 3, 6. I'll start with the domain. Again, my denominator, 2x minus y, cannot be 0. So y is not equal to 2x. If I were to sketch in a dotted line y equals 2x, that's the excluded value, I would have, let's see, 2, 4 would be on the graph, 4, 8 would be on the graph, 0, 0 would be on the graph. Oops. And I just said I was going to sketch that as a dotted line, and then I started drawing it solid. Let me fix that. So there's that line y equals 2x. And we want to exclude that. Our domain is everything else. All right. I'm approaching the point 36. Now notice that y value is exactly double that x value. So this point is on the line y equals 2x. 3, 6 would be about here. So 3, 6 is a boundary point. When you have a boundary point, you should expect to get something funny happening when you try to substitute in your value. In this particular case, if I try to substitute, what am I going to get? Well, let's see, I'd get 2 times 3 squared plus 7 times 3 times 6 minus 4 times 6 squared over 2 times 3 minus 6. Denominator is clearly 0. And that numerator, let's see, that would be 2 times 9 plus 21 times 6 minus 4 times 36 is also 0. Hopefully you remember that 0 over 0 case. It's what we called an indeterminate form. And anytime we have an indeterminate form, we have to do additional work in order to figure out what the limit's going to be. Right? Now you learned in Calc 2, probably, maybe Calc 1, depends on where you took your calculus, but you've learned in a previous calculus class that when we had functions of one variable, there was this really nice thing called L'Hopital's rule that we sometimes used on these indeterminate forms. Unfortunately, we cannot use anything like a L'Hopital's rule here. First of all, we haven't even talked about how to find derivatives of these kinds of functions. But secondly, I'm going to be honest with you, there is no equivalent for multivariable functions. There's no such thing as L'Hopital's rule for a function of several variables, so we're stuck without it. Instead, I'm going to say let's do some algebra. If I were to factor my numerator, and I'm just going to leave the denominator the same, 2x squared would be 2x times 1x. And let's see, 4y squared, a couple different options there, but I want to get a 7xy in the middle. So I think I'm going to go with a 4y and a y. That way I'll have 8xy and 1xy. If I play my cards right, I can get a 7, right? Make that a positive and that a negative. 8xy minus xy would be 7xy. And there's that negative 4y squared. So I think we're good to go. And I can see that I'm able to cancel out that common factor in the numerator and denominator. And with those canceled out, if I now try to plug in, I'm going to get 3 plus 4 times 6, or 27. So that limit is 27. I'm going to ask you to remember back again to when you did these kinds of problems back in Calc 1. When you had a function where the y value didn't exist, or in this case it would be the z value that doesn't exist, right? When I actually tried to plug in 3, 6, I got something undefined. But the limit does exist. Do you remember what happened? Usually in Calc 1 you're taught that that's like a puncture or a hole in the graph. There's a missing point there. That's exactly what's happening here as well. At the point 3, 6, the graph thought it was going to have a z value of 27, but it's like a little hole or a puncture there. That point is just missing from the graph. So the point 3, 6, 27 is missing from the graph. All right, let's talk a little bit more about this, and I want to take a look at a graph on this one as well. This point, because it was a boundary point, turned out in the limit to have a finite limit, and so there was a little missing point. And in fact, that's going to be true for every single point on this boundary, right? All of these are going to have z values that are just sort of missing right above them. So what I'm going to end up seeing if I graph this is my resulting function, z equals x plus 4y after I simplify. But it should have a little strip missing. Technically, it's an infinitely thin little strip, but no one's particularly good at graphing things infinitely thin, so I think we're going to be able to see it in Maple. But that's really what's happening. So as far as the graph is concerned, it's going to be the graph of z equals x plus 4y, which notice that's just a plane, isn't it? X, y, and z all to the first power. With a missing stripe, if you will. Above the line y equals 2x. All right, let's take a look again over at Maple and see if we can see that. Let's see, I guess I didn't actually look at that one. Let's take a look at this one. Here it is. Here's my function, plotted from -5 to 5 on the x-axis, -10 to 10 on the y and the z. I threw in a few extra points, set my axes to normal, and at least for right now, my style is set at surface. Here's the graph, and notice it does indeed look like just a flat plane like I was expecting, but you can clearly see that little missing stripe. That is actually the line y equals 2x. It looks a little steeper than that just because notice I used some slightly different windows on my x and y axes, but you can definitely see that little missing stripe. In fact, if I did a constrained scaling over here, it would probably look a little bit better. There's that missing line from the plane that's right above the line y equals 2x. All right, let's do one more example here of this type, and then we'll be at a good point to kind of pause and go on to the next video after that. In this next one, I can take a look at this function, and I can see that there are actually two things that I have to be concerned with as far as the domain is concerned. I can't have a negative under the radical, but I also can't have a 0 in the denominator. So my domain is going to have two issues. Let's do the domain here. First of all, x plus y is going to have to be greater than or equal to 0. I can't have a negative under my radical. So y is going to be greater than or equal to the opposite of x. Secondly, x plus y minus 9, the denominator, cannot equal 0. So x plus y can't equal 9. So a couple things going on there. Let's see if we can graph what that would look like. All right, y is greater than or equal to minus x. minus x, y equals negative x, is just the line with slope -1 through the origin, right? And notice that's greater than or equal to, so I'm going to draw that as a solid line. That's the line y equals minus x. And y has to be greater than or equal to minus x, so I'm only looking at the parts above that line. Now before I actually draw that, I'm also going to notice that I have to omit the line x plus y equals 9. That would have x-intercept 9 and y-intercept 9. So I'm going to put in as a dotted line. Oops, I missed it by a little bit, you get the idea. X plus y equals 9. And I have to skip over that. So my actual domain is going to go between these two lines, and then skip over the line, and then everything to the right of it. All right, we were supposed to be approaching the point 4, 5, and notice that since 4 plus 5 does equal 9, that once again is going to put me right on this graph. 1, 2, 3, 4, 5 would be about there. Four, 5 is a boundary point. It's on the dotted line. So I'm expecting problems, and of course, pretty quickly I'm going to get them. If I actually did try to substitute, putting in 4, 5 would give me square root of 4 plus 5 minus 3 over 4 plus 5 minus 9, and that's 0 over 0. So I see that indeterminate form again. Anytime I have an indeterminate form, it tells me, go ahead and try some algebra. You may very well be able to find a finite limit, but you're going to have to work a little bit for it. So let's do that. Let's take the limit of our function. Once again, I'm going to ask you to kind of call on what you know back from Calc 1. When you did limits with radicals in them in Calc 1, usually we use the trick of rationalizing either the numerator or denominator, wherever the radical happened to be. In this case, it happens to be the numerator. And the way we rationalized was to multiply by the conjugate. We're going to do that here as well. I'm going to multiply by the square root of x plus y plus 3. And of course, I can't change the value of my expression, so I have to multiply by the same thing on the bottom. So really multiplying by a form of 1 here. When I do this, my numerator acts as all wonderful conjugates do. When I multiply, those radicals will essentially undo each other, and I'll just get x plus y. The outers and the inners are opposites, so they add up to 0, and then I'll get a minus 9. I'm not going to multiply out the bottom because I'm looking at that x plus y minus 9 thinking, hey, I'm going to get to divide you out in just a minute. And that's exactly what we want to do. And that's just going to leave a 1 up top, meaning that I'm going to now be able to try and plug in my 4 and 5 again. And nothing bad happens this time. I just get 1 over 3 plus 3, or 1/6 for my limit. Okay. So very similar to what we had in the last problem, in that geometrically, you'd have some graph. It's not going to be a nice plane this time. It would actually be the graph of this. This is what's left after I simplified. It would be the graph of z equals that. But in that surface, right above this dotted line, there'd be sort of a missing stripe of points. And one of those missing points would be 4, 5, 1/6. So my graph will be the graph of z equals 1 over the square root of x plus y plus 3 with sort of a missing stripe. Above, what was it again? X plus y equals 9. Our point, 4, 5, 1/6, is on that missing stripe. Sorry. All right. This one I actually couldn't get a domain in Maple. Sometimes the window that you pick will obscure the missing stripe. And I was playing around a little bit and I couldn't quite make it work. We know that missing stripe is there. I'm not going to be able to show it to you very well with Maple, but I do want to show you the graph real quick because we can easily see this domain piece, that there's nothing to the left of the line y equals minus x. So let's see, here we go. Here is our function that we started with. Again, I put kind of a lot of points in here, set my axes to normal and my style to surface. And what I'm getting is, it's not quite a plane, right? It's sort of curved up. You can see it's fairly flat over here, but it curves up at the edge, right there. If I take a top-down view, it looks like a jagged line, but this is just really the line y equals minus x. You can see this would be the third quadrant, right? So this is the second, this would be the third quadrant, so this is the second and the fourth. The line y equals minus x. And it definitely cuts off there. Now, I'm not able to see that missing stripe that I should see. And again, this is just a casualty of technology. Just like on your calculator, Maple essentially plays connect the dots. It's just really fast and really sophisticated. So if it saw a point on this side of the stripe and another point on that side of the stripe, it essentially connected them and jumped right over the stripe. And I was not able to figure out the perfect window to force it to see those missing points. Up here, you'll actually notice, remember the missing points here where y equals 2x? I literally picked my y values for my window to be double the x values, and that's how I got it to see that missing stripe. I cannot figure out a good way to do it on this line one, so if you figure that one out, you guys can let me know. I'd appreciate it. All right, sorry, I know this was a bit of a lengthy video, but that gets us to a good point to pause, and we'll continue with this section in the next video.